So I mentioned power. Let's talk about electric power. This is the rate at which energy is transferred. Electrically, power equals current times voltage. So power is equal to current times voltage. Power is measured in watts. All right, so I just mentioned that we have so much power that these resistors can handle. So we're going to be able to calculate that. So power is measured in watts. Power would be the watts, the rate that like a battery is moving energy out of it and delivering to the rest of the circuit, maybe to a light bulb. Light bulbs have power measuring, which are numbers which tell you how much power they're dissipating, how rapidly they're moving energy through them, which is directly related to ones to how much light they produce. So this is a common concept. Now what I can do is I can combine this with my Ohm's law. This is some of the homework here this week too. So I know that power is current times voltage. And I also know that current is voltage over resistance. So I can substitute voltage over resistance. So I just substitute this in for current. So power, V times V, is V squared over resistance. Okay, so I have that power is current times voltage, which is great if I know current and voltage. And if I had a resistor that has a set value and I measure the voltage across it, I could use this to find the current. I could use Ohm's law to find the current and then find power. But I can also, by doing the shortcut, just go, hey, if I measured voltage, I can square it, divide by resistance, and I know the power being dissipated by that resistor. So this is a good thing to use. You got to do one measurement, one calculation. Otherwise, I do one measurement, and another kind of do two calculations. So it's just kind of a shortcut. Or power equals current times voltage, and I know voltage equals current times resistance, right? These are just two expressions of Ohm's law. I can plug that in. Plug this in, and I end up with current squared times resistance. So that means if I have my resistor in there, it's a 1/4 watt resistor, I can double check and make sure, if my voltage gets too high above that resistance, my power will go over 1/4 watt, 0.25 watts. Those resistors I passed you, and it will get too hot, and it will start to smolder and get hot and uncomfortable. Now, I mentioned that I have a circle out there you can pull down. It will have all three of these equations, plus one for how to find resistance, power and voltage, resistance and power and current. And it will have the Ohm's law equations. Everything we've covered today is in that, so feel free to use it. If you don't like doing algebra, if you're fine doing it, or just want to write the equations down, whatever's most comfortable for you. All right, now, let me just take a little mathematical second here for the multipliers, because I know I've been using them, and I know you've probably seen them, but let's just stop. So my metric multipliers. I'm going to start in the middle of my table here. If I don't have one, then I'm multiplying by 10 to the 0 power, or times 1. That's my amps, my volts, my watts, whatever. Now the one down we've used here is milli. Little m is milli. That is times 10 to the minus 3 power. So it takes 1,000 milliamps to make an amp. It takes 1,000 millimeters to make a meter. It takes 1,000 milligrams to make a gram. I mean, all those, they're consistent. If I go above this, and your resistor was measured in this, it's kilo. So that's times 10 to the third power, minus third. So this is times 1,000. I'm sure you've seen it somewhere that, 1,000 meters is a meter. 1,000 ohms is a kilo ohm. Okay. We really need the 2 on either side of these now, too. Anybody know what's bigger than a kilo? Yeah, it's mega. Here's what's really important about this. Okay, this is times a million. You can also think of m as million if you'd like. Do note, we have milli and mega. They are both m's. You cannot write these. I had somebody a couple years ago. Well, my little m's and big m's look the same. They can't. You have to distinguish these. Because that's a billion times difference. A milliamp's great. A mega amp is got applications, but not around here. Mega ohm is an actual resistor we can have and we will use at some point here. It's not an uncommon resistance. A milliohm is a resistor you can have in precision applications, but probably nothing in here. If anybody goes for like a condenser mic next semester, it's second semester audio class maybe, but you get little. Above this, we won't use much, but you hear the term giga times 10 to the 9. That's a billion. Anybody know what's below milli? Micro. Micro. So we have another M, but I've ran out of M's. No, I didn't, because we like Greek. So use Greek M. Micro. Looks like a U with P-tail. By the way, most electronics, because it's more expensive to type this, they'll just use a U, and they need micro because they don't want to type the little tail. Let's put a U, and they'll go, man, this close. But it means micro. They start to get hard to write out. You can see why we use micro. If you try to enter this and keep track of all these zeros, the odds of getting off by a zero, one spot or the other is quite high. Type in your calculator. I'm going to go ahead. The 2 below it, we will see once we get to capacitors, but we're not there yet. But I'm going to go give them to you. Do I know what's below micro? Oh. Nano. I'm not even going to try to write that. And below that, pico. Now, more than likely, you can't put 12 values after your decimal point in your calculator, even if you want. So your only way to enter these is to learn to use scientific, engineering, not scientific, engineering entry in your calculator. So it is more than likely either a capital E or 2 capital E's. Or some of them will now have a times 10 button on them. Figure out how to do it. All your calculators are different. I will try to help you with it if I can. I mean, I'm sure I can, but we may have to sit there and look at it in a second. So if I want to enter let's say 12 microamps. My choices here are to go 0.000012 amps, or I can type 12 on my calculator, or times 10, or the E, whichever way it is. Do not use the small e. The small e on your calculator is the natural number. It's like 2.7 something. Second most common number in nature after pi. Don't use it because it'll be wrong. So the little e, don't use. That's for different classes. Big E, yeah. There's a good chance this negative is not the minus sign. A lot of calculators will have a little parenthesis with a plus and minus inside. That's just the negative number. Some of them do use the minus sign. So you guys got to play with your own calculator, make sure it's working right. I'm not trying to confuse it. I'm just saying you got to. And because of my experience teaching this class, a lot of people, like I said, we'll get weeks in and they still don't know how to get numbers in and out of the calculator. So have your calculators out here in class working with me. That way if you get those, we get them fixed. It's so we had struggling with that months after the fact. Yeah.
Do like all basic calculators?
Any scientific calculator will. A basic, just like addition, subtraction, whatever calculator probably won't. It'll be scientific. If anybody has your TI-84 from high school algebra around still, it's total overkill, but it will do it. You can go pick up something like a TI-30 or TI-35 for like $10 or something like that, 10 or $12. I have some in here I'll let you use in emergencies, but I don't have enough to go around for everybody all the time, so have them. If you use your phone, I don't care if you use it in class. I'll say an actual calculator is faster than your phone, and you can't use your phone on the exams. One time I tried to be nice. The first time I was, somebody said, "I like looking up, trying to look up answers." So, if you do use your phone, most of them, if you hold it straight up and down, just gives you a standard calculator. If you turn it, you get a scientific calculator. It still doesn't work as easy as an actual just normal calculator experience. So, like I said, don't get carried away. $10, $15 scientific calculator does this. Needs square root. You need like a 1 over x button or x to the minus 1 button because we'll start using a lot of that once we move it. Actually, sure, we can talk about resistors. All right, I'm going to stop for today. I think we covered quite a bit. I've recorded all this, so it's all going to be available out on Blackboard like all the other lectures out. If you need to review it. Just a reminder what I said at the beginning. Hey, I'd go in on Sunday or Monday before class and read what we're going to do the next week. At least give it a cursory read, okay? If you don't read the text in depth till after lecture, fine. But if you read it, go, oh, we're going to be talking about this topic, and then you know what you can do. Lab this week is going to be doing Ohm's law. You will take a resistor. You will change the voltage and turn it up and up and up and measure the current. And then we're going to create a graph in Excel with it. Couple things. We will do lots of graphing in Excel. Now, first of all, I don't care if you use a different program to get your graphing. I will support Excel because all the computers in here have Excel on it. Plus, the college pays for Excel 365. So every one of you has access to it. I personally, most math engineering people don't really like Excel. There are other better programs, but it's not really available to people outside of those fields. So Excel is going to be good because it's also going to teach you stuff that's going to be relevant. No matter where you go, if you can do a little Excel here and there, great. Let me just give you this for everybody in here. Graphing. You know, you've heard pictures 1,000 words. The graph is a picture. It takes me and lets me do one picture that you can view and see and understand rather than writing several pages of description. But that means that the graph needs to be clearly labeled as to what it is. So I'm going to make you do these correctly. Okay, a lot of instructors will do things like put problem number whatever here. No, don't do this. They make it like a real one that's going into a paper or something. This isn't hard. But on here, I'm going to come down and I'm going to put something like a voltage or current or whatever we're going to measure this week. I'm making these up. But if this is voltage, I might just put something like resistor voltage. Make it clear in English. Put parentheses and put the units. Again, doesn't mean anything without the units. And I don't know whether you do volts or millivolts, it should tell me. Warning, if you measured and finished your table and early on it's millivolts and then moves to volts, great. You do the graph. They all need to be volts or they all need to be millivolts. So you have to adjust them and make sure they're all the same units. So your graph will look funky. On this side, you can enter something. Maybe I want to do resistor current. This is really hard to write this way. Probably something like microamps or milliamps. I'll put milliamps there. Okay, on the top, do not give me problem such and such lab such and such. I know that, okay? Give me some descriptor that tells you you know what the heck you just did. Biggest complaint I have, you create a graph and put a graph in there and say, is that what you wanted? The graph should be in there telling me what you just understood and figured out from class. It's your expression of what I learned from this. If you don't understand the graph, then you keep working on it until you get it understood. I might do something like, experimental. I think I spelled it wrong, but we'll go with it. Ohm's law. Give it something. It's a picture. It should stand alone. If I look at a picture, somebody took it outside, I shouldn't have to read 10 lines of paragraph. I shouldn't have to go in. I should go look and see what it is. Maybe I have to read a caption to understand what it is. I'm seeing it against the snow background. A caption. Data. Use the scatter plot. I will show you how to do all these in lab. I'm just going to give you a general thing here. Some of you are going to go create at home or whatever. That's fine. That means you have little dots. Don't connect the dots. That's how you do little kid drawings. That's not how we do. I mean, for one, it looks janky because the line goes all around. But the other is you're kind of lying. You're saying, hey, I know all this information. No, you don't. You only know the dots. You don't know what's in between. You just assume what's in between. It's called interpolating. Then I tell you, hey, add a trend line. This is a thing in statistics called the best fit line. It's a line that fits the data the best. There's different scientific ways of going about it. But it'll automatically do it if you say hit one and make sure it's linear. And then it's going to create a line that looks like this that fits the data pretty well. So there's data on both sides. It's the line that actually represents, hey, this is the best representation of this data. Now, it gives you an option to click a little button that says add an equation. Add the equation. There'll be a little equation that looks like a line equation. Remember, line equations are like y equals mx plus b. You're going to get something like that up here. It's going to be like y equals 1.035x plus 0.02 or something like that. This is the slope of the line. That's the intercept. If you're doing Ohm's law, that intercept should in theory be 0 because we have 0 voltage, you get 0 current. But I'll tell you when you do your data, you're going to have some little number over there. It's not going to be perfect. It'll probably be really tiny. It'll be really good, but it won't be perfect. Slope. Rise over run. Current over voltage. The slope here is the change in current over the change in voltage, which is 1 over the resistance, because resistance is voltage over current. So I can take my slope and go, hey, this was my measured current, or my measured my measured resistance, actually my 1 over the measured resistance. And then I'll compare it against my what I measured with the ohm meter and what the resistor says. That way you can go through, go all the way full circle. I can measure my resistor, I can build it, I can prove Ohm's law works, I can make a little graph and pull that off. This semester our graphs, we're limited here and there, but do them because you're learning. Next semester, every single thing for those of you go through have a graph. And usually I look at it and that's frequently like 50 or 60% of the grade. So I can read the grade. If you did everything right, I know what the graphs look like. Okay. I'm gonna quit. They walked out on me because they had class, and that's okay.